Design criteria is the bit rate, and the bit rate is associated with dispersion, and the calculation of this bit rate is known as rise time budget. So, as we all know, we being the electronic engineers, the electronic systems are usually categorized as overdamped, underdamped, critically damped, and undamped systems. We have already learned this in the control systems, and most of the systems comes under the overdamped systems. So what is this overdamped systems? Overdamped systems are those systems in which the output is always less than the input. It never overshoots the input. So always the output is always less than input. It never outshoots the input. So what is rise time? Next is the definition for rise time. The rise time of a system is the time taken by that system to reach from the 10% to 90% of the steady state response, and the rise time is denoted by the letter TR. As you can see from the figure, there is an input signal which is marked in red, and the system response marked in yellow, that is when it reaches from its 0% value to the 90 percentage of the output. Okay, the time taken to reach from the 10 around 10%, the lower value 10% to the 90 percentage of the higher value, that time period is known as the rise time, and it is denoted by the letter TR. And there is another notation for TR. The rise time is always inversely proportional to bandwidth. So ideally, for ideal system with infinite bandwidth, the rise time is 0. So that means the system can instantaneously reach to its steady state without any delay. As you can see from the figure, there is no delay of this output to reach to a steady state. Okay, it can instantly reach to its 100% value. And when the rise time is in nanosecond, we have an equation for TR is equal to 350 divided by bandwidth. So in a communication system, we have each of these modules: transmitter module, the channel, and the receiver. So each of these systems, each of these electronic system have their own rise time. Rise time, like the time taken for a system to reach the steady state response to a 90%. So each of the system has their rise time. So the total rise time will be the collective rise time of each of the transmitter, receiver, and the channel. So now we'll see the different equations for the calculation of rise time budget. So as already mentioned, the rise time accounts for the rise time in the transmitter side, the receiver side, and the channel. Okay, so in the channel we have in the channel we're mainly using the optical fiber. So the rise time in the optical fiber are mainly due to fiber material dispersion and fiber modal dispersion. So now we'll learn in detail what are the different rise time associated with transmitter, receiver, fiber modal dispersion, fiber material dispersion, how we can account it. Okay, so first rise time of the transmitter. So in the rise time of the transmitter mainly depends upon the transmitter electronic components, the driving circuits, and other electrical capacitor associated with the transmitter. So whichever components, electronic components that are related in the transmitter, all of these accounts for the rise time, and mainly the optical sources. So if you are using LED as an optical source, it is mainly in few nanoseconds, and if it is a laser, it is mainly 0.1 nanosecond as the rise time that we take into account for the transmitter rise time. So now we'll see what is for the receiver rise time. So receiver rise time, similarly, these will be the electronic components that are associated in the receiver. And so as already mentioned, if the receiver rise time TR is in nanoseconds, we can use the equation 350 by B, where B is the electrical bandwidth of the receiver in megahertz. Now the next factor is the modal dispersion. Okay, modal dispersion, we've already learned about what are the different types of dispersion in your first modules. So as we all know, the modal dispersion is absent in single mode fibers, but it can be taken in account for multi-mode fibers. So the dispersion associated with the material is given by, or the modal dispersion T mode is given by T mode is equal to N1 delta square L raised to Q by 20 root 3 C, where N1 is the refractive index of the core, delta is the differential refractive index, and it is given by N1 minus N2 by N1, L is the length, and Q is a constant which has a value ranging from 0.5 to 1. We generally take the value as 0.7. So next is the rise time according to the material dispersion. It is given by T mat is equal to modulus of d mat sigma L, where d mat is a dispersion parameter of the fiber, sigma L is RMS spectral width of the source, and L is the length, as we have already discussed. So the total rise time of the length of a point-to-point link communication system is given by T system is equal to square root of TT square plus TR square plus T square mode plus T square mat. That is the rise time of transmitter receiver due to material dispersion and due to modal dispersion. So calculating all these, we get the total rise time of the system. And how this rise time of the system is associated with the bit rate is that we'll be either using different types of formats for the data transmission, like non-return to zero or the return to zero. When you're using non-return to zero, the total rise time of the transmitter should be always less than zero point 0.1 zero point 0.7 of TB. TB is the bit rate. Okay, so similarly for return to zero, it is given by T system is always less than 0.35 TB. So in the transmitter side, if you're using non-return to zero polarity or return to zero polarity, the total system rise time is given by T system is less than 0.7 pulse or TB. TB is a bit duration of the pulse of for that specific data, right? Similarly, if you are using return to zero polarity in the transmitter side, the total rise time is given as should be less than 0.35 TB.